In this lecture, we are going to combine what we learned about in the previous lectures and build up the full Arima model. Before we do that, however, let's first discuss what we get when we combine the AR and the MA models only, which gives us the Arima model. After that, we'll discuss what the I component means, and then combine that with the Arima model to give us the Arima model. So I think the Arima model is pretty straightforward once you understand the autoregressive and moving average parts separately. The Arima model simply adds them together. Therefore, you would use this model if you believe that each point in the time series is linearly correlated with both past points in the time series as well as past errors of the model. Note that the abbreviated form of this model is Arima PQ. This is short for autoregressive moving average model, where the autoregressive part has order P and the moving average part has order Q. Now that we know what Arima is, let's talk about Arima. The I part in Arima stands for integrated. Therefore, the full name for this model is autoregressive integrated moving average. What is interesting about this model is that the integrated part has no parameters, so the way it looks is very different from the autoregressive and moving average parts. So how does the integrated part work? To understand the integrated model, we have to understand differencing. Suppose that we have some time series, y of t. To perform differencing on this time series, you would define a new time series, delta y of t, which is defined as y of t minus y of t minus 1. That is, for each point in the time series, we subtract the previous data point. Now, a good question to ask is, why would you want to do such a thing? In fact, this is not the first time we have seen differencing in this course. We have seen it twice previously. One time we saw differencing is with log prices. When we perform differencing on log prices, we get the log return. As you know, this is a pretty important quantity in finance. Another time we saw differencing is with the Holt-Winters model. The first difference of the level is used to estimate the trend of the series. In other words, one way to think of differencing is detrending, or in other words, separating out the trend. In fact, we see this in stock price time series as well. After taking the first difference of the log prices, we get the log return, which is generally a noisy signal that fluctuates around a value close to 0. So why do we want to difference our time series? The reason for this is, when we use Arima models, that is, autoregressive moving average models, we want the time series we use the model on to be close to stationary. Now, what does stationary mean again? At a high level, it means that the distribution of your signal does not change over time. There are more details we can discuss regarding stationarity, but we will leave this for a later lecture. Stationarity is a nice property because it means that various statistics, such as the mean, variance, and autocorrelation, will remain constant over time. This is a good thing when you're trying to fit an Arima model, because remember that each window of the time series is like another training point when you are fitting the model. Now this slide is optional, but I want to elaborate on the previous point a bit more. Recall that earlier, I talked about training your own autoregressive model using scikit-learn by first building your dataset from the time series. As you can see, this dataset is built out of sliding windows from the original time series. First, the window covers y1, y2, and y3. Then we slide it over one step. Now the window covers y2, y3, and y4. Then we slide it over one step again, and so on. One important aspect of machine learning is that the data in your dataset is assumed to all come from the same distribution. If it didn't, then you wouldn't be able to learn anything. Remember, machine learning is pattern recognition, and pattern recognition is machine learning. If we mess up the pattern, then we mess up the machine learning model. Imagine, for example, that we had our table of salary data. Suppose that we work at a software engineering company, and all of the coworkers who helped you fill in your spreadsheet were software engineers. Then all of a sudden, one of your buddies from the marketing department fills in their data on the spreadsheet. But unfortunately, marketers get paid differently than software engineers, and so it's likely that the distribution for marketer salaries is different from the distribution for software engineer salaries. Your model might see this data point as an outlier, which might bias the results. So that's why we want all of our data to come from the same distribution. Otherwise, what we are trying to learn won't make much sense. If we're trying to predict software engineer salaries, we don't want data from people who are not software engineers. For us, we have a time series, and each position on this time series makes up a new data point in our training set. If we would like all these data points to come from the same distribution, then the time series being stationary accomplishes that, because that's exactly what stationarity means. So let's get back to stationarity. Now we know why stationarity is good. Well, it turns out that differencing a time series often helps to make the time series stationary. Now remember that when you're working with real data, nothing is exact and you're always approximating. Yes, we know about volatility clustering, so we know that the variance of the log return can fluctuate over time. Does that mean we throw out Arima completely? The answer is no. And sometimes we may even find that we have to difference twice in order to get a time series that looks somewhat stationary. Usually, however, we don't difference more than twice. Okay, so what does differencing have to do with Arima? We say that a process is ID if it is stationary after being differenced d times. An ID process is a process that is integrated to order d. Once we have this, we can define the Arima model. The Arima model has three arguments, P, D, and Q. As you recall, P refers to the autoregressive part, Q refers to the moving average part, and now we know that D refers to the integrated part. Thus, Arima PDQ is just a model where we have differenced the original time series, D times, before applying the Arima PQ model. So that's why the I part of the Arima is strange. Unlike the autoregressive and moving average parts, which have some formula that you can use to make predictions, the integrated part describes an operation that you perform on the data. Now that we know what the full Arima model is, we can see that all of the previous models we've discussed are actually just special cases of the Arima. For example, Arima P00 is an ARP process. This is also the same as an ARMA P0. Similarly, Arima 00Q is an ARMA 0Q, which is also an MAQ. Arima 0D0 is an ID. One interesting special case is Arima 010, or equivalently I1. This is what is known as a random walk, which we discussed previously. This model looks as follows. It says that delta y of t is equal to epsilon of t, the noise at time t. Why is this a special case? Well, it just means that there is no autoregressive part and no moving average part. By omitting these two, all that we are left with is noise. The left side, delta yt, is just the differenced time series. Equivalently, it says that y of t minus 1 is equal to the noise at time t. If we move the y of t minus 1 to the other side, we get that y of t is equal to y of t minus 1 plus epsilon t, which is exactly the random walk formula we discussed earlier. It says that whatever process in nature leads to our time series, it takes the existing value, y of t minus 1, generates some random noise, epsilon t, and adds them together to get the next data point yt. Another way to view this, if we think about financial quantities, is this. Suppose our dataset is a time series of log prices. Then the first difference is the log return. A random walk says the log return is just epsilon t, the noise. What this tells us is that there is nothing about the log return that is predictable, except for the expected value of the noise. It does not depend on any past values, which is what an autoregressive model would tell us. It does not depend on any past noise terms, which is what a moving average model would tell us. Instead, a random walk says that the log return is purely noise from a single point in time, and hence completely unpredictable aside from the mean of the noise. Therefore, if we later fit an Arima model to a stock price time series, and we find that the best Arima model is Arima 010, this tells us that the data follows a random walk, and the return can't be predicted using previous values in the time series.